Welcome to this second lecture on power amplifier design, 2. We have already seen the nonlinearity, its effect that it creates third order intermodulation product. Now, we will quantitatively characterize that third order intermodulation product in this lecture. Now, in that we have started with that two tone test. They are assumed that the second tone is absent. So, that means you put AT is equal to 0. I am recapitulating that VI was this here and VOT that was this. We are considering up to third order nonlinearity, and there if we make this A2 is equal to 0, again we can, this was our harmonic terms. I am writing here, you put all A2 is equal to 0 value. This is again recapitulating. Now, if we do that A2 is equal to 0, then output at the desired frequency, I have now only one, by putting A2 is equal to 0, what I made, that I have one frequency, that frequency is omega 1. So, output at omega 1, if you look what is the output at omega 1. So, you see the output at omega 1 will be this, you see this part is absent, but this is there, this is coming from that third order nonlinearity. So, what will be the output of this? A1 capital A1 plus 3/4 small a3 capital A1 cube. So, that is what I am saying, output at omega 1 is this. At 1 dB gain compression point, we have this definition, actual gain by linear gain is equal to minus 1 dB. So, I put this actual gain, that is this, but had this been linear gain, then this was not there, this was simply 1, and that according to this definition is minus 1. So, by that I have related the A1, its value, the A1 is the input signals gain, that is given by this thing, an important result. So, if I know my system, my nonlinear system, so I know A1, A3. So, you do this, if I know A1, A3, I can calculate what is my gain compression point. That means, what is the level of the input signal at which I will start getting gain compression point. Now, also let us calculate the fractional second order IM product, intermodulation product. What is second order intermodulation product? Output amplitude of the second order intermodulation output divided by amplitude of fundamental output. So, second order intermodulation in two tone test, when we made A2 is equal to 0, we do not have, but this is the harmonic term, this is the actual term linear amplitude of fundamental output. So, I get this. So, intermodulation product of second order IM2, this I am calling fractional because I am normalizing with fundamental output, that you see varies linearly with this A1. A1 is the label. So, IM2 varies linearly with the label. Now, fractional third order IM products, IM product is this and the fundamental one is this. So, it is A1 square. So, I can say IM2, just before what we have seen, intermodulation second order intermodulation product fractional part rises linearly with input signal, because previous one we have seen that it is simply proportional to A1. These are constant, system constant, but IM3 rises linearly with square of input signal. So, that is the thing. Now, if I convert this same thing to dB scale, slope of IM3 is twice that of IM2. Because of this A1 square, I can say that slope of IM3 is twice that of IM2. So, if I put it in that transfer characteristic input output in dB scale, then you see the linear one is going like this, second order is going like this, the third order its slope is twice. So, it will go like this. So, you see that at a particular value, if I say that it will be significant or it will be significant to the input signal, you see that second order is always lagging, but this third order intercept, since its slope is much higher than second order intermodulation. So, at some high level it will catch up and it will be of the same level as the desired signal. At low input IM3 product is small, so it is negligent, but IM3 slope is thrice. So, at high input it catches up. Nth order intercept point, let us generalize the concept. The input signal level where the extrapolated values of the desired signal and the nth order intermodulation product are equal is called the nth order input intercept point S11 P1. It is a signal level, that is why we are designating it by S. But what is the concept? That at this value of the input, my intermodulation product is catching up, that means becoming same as the original signal or linear signal, where the extrapolated values of the desired signal and the nth order intermodulation product becoming equal. That means, the linear signal that is becoming equal to the intermodulation signal. So, there can be input nth order intercept point, similarly there can be output intercept points. Output points are called YP, input intercept points are called IIP. Generally YPs are more useful to deal with, because we are amplifier output we are concerned with, but if intercept point is specified in terms of input, you can also do that. Now, let us calculate these values where it will catch up. So, what is this? Definitely from the definition I can say that SI P1 are values where fractional intermodulation product should be 1, because fractional, if you remember, if you see your notes, fractional intermodulation product, what we have defined, that where it is the intermodulation product of nth order divided by the fundamental signal level. So, if where they are touching at intercept points, they are becoming equal. So, at that point fractional IM means 1. So, I can do that because already we have done that intermodulation thing. So, if you do that, you see that at this value the second order intermodulation is becoming. So, this is the value where second order intercept point is coming. Here the third order intercept point is coming at this value. So, this is given by A1 by A2, this is given by A1 by A3. So, A1, if you remember, that is the linear part, A2 is the coefficient, my system coefficient for second order nonlinearity, this is third order nonlinearity. Now, we have already said that we are concerned about IIP3, this 1 dB, this d should have been smaller d, but in PowerPoint I think in the title page it comes like this. Now, comparing input 1 dB gain compression point, and because we have already seen what is input 1 dB gain compression point, if you remember, this was our thing, and now we have seen AIIP3. So, if we compare, the comparison is this, that AIP3 is 1 dB gain compression point plus 9.6. That means, let me show those graph. So, I can say, or so you see, this was our point of, this point was our, this was our 1 dB gain compression point. let us say in the input side. What that is saying that if I go further 9.6 dB, my third order intercept point will come, and at that point the linear signal and my third order intercept point, they are becoming equal. You see, the message is, this is simple mathematics, but the message is that the third order intercept point that comes when input signal level corresponding to the 1 dB gain compression point is added by 9.6 dB. Please remember, this is a dB relation. So, if you have output intercept point, this is the second order output intercept point, it is given by this. This is the third order intercept point, output third order intercept point, this is given by this. So, since we know our system, that means we know A1, A2, we can always calculate this. Now, what is the utility of third order intercept point? You see that this is my actual linear graph. Obviously, this is extrapolated here because already it is going to the intercept point. Now, I know that this slope, here I am showing the red one is showing the third order intermodulation signal. So, at this point you see it is catching up. So, this is the third order intercept point, and you see this slope is 1, this slope here it is 1. Now, what we will do, we will show by mathematics that slope of this signal is 1. So, I can say, you see, this AC is equal to DC, because if slope is 1, then DC and AC they are equal, but I know what is DC. DC is nothing but POIP minus POMDS, because this is the point you see POMDS. So, this is here you write POIP minus POMDS. Also, we know that slope of this is 3. So, BC, this slope is BC is 1/3 DC, BC is 1/3 DC. Now, that is 1/3 this. So, from this I have found AC, I have found BC, you see I have found AC, I have found BC. So, I can find what is AB. AB is 2/3 POIP minus POMDS. So, also slope of PF1 signal is 1. So, from that I can also find out that AB is nothing but equal to B. What is B? This. So, this is 2/3 like this. So, from this actually I have an important relation that, or let me go later, that B is the range that previous you see B. So, what is B? B to E. So, this is the range where the third order intercept point is coming. That is what I am saying. B is the range where IMT product has just started coming. So, I now know that this is the range that I should avoid, because now third order intercept point is coming. So, I should stop. That means, I do not need to go up to the 1 dB gain compression point. I need to see that when this third order intercept point has started coming up, then I need to stop, and that is my, that is called spurious free dynamic range. So, my actual dynamic range is not this. Previously, we have given the definition of output dynamic range with this, that OIP that our actual thing, that 1 dB gain compression point minus POMDS, but DRF we are saying it is here, and that we can POIP, we have expression POIP, then this POMDS, for that we have already derived the expression minus 174 plus all those. So, that if I put, so from a, if in any system POIP specified, I can find the spurious p dynamic range. Usually this spurious p dynamic range is smaller than the dynamic range for a single tone system. So, that means if I have a single tone, I can use dynamic range, but if I have a band of frequencies and if I have nonlinearity in the system, then I know that not all that full dynamic range is usable. If I restrict myself within the spurious p dynamic range DRF, then I know that I will never go to nonlinearity. So, let us see an example of dynamic range. An amplifier has available power gain of 40 dB, 500 megahertz bandwidth, noise figure of 7 dB and 1 dB gain compression point is given at 25 dBm. Calculate dynamic range and spurious p dynamic range assuming detector SNR requirement to be 3 dB. That means, what I said that above noise level, if it is 3 dB more, I say okay, there is a signal. So, solution is given here. We can first find out what is POMDS minus 174, this is the bandwidth, then these are given the noise figure, etc., etc. So, you see that POMDS is minus 37 dBm. So, if any signal is minus 37 dBm, then my system detects it. So, dynamic range we can easily get, because PO 1 dB gain compression point 25 dBm that is specified. I have calculated this. So, minus of minus this. So, dynamic range is 62 dB, but also calculate what is third order intercept point, because you will have to calculate spurious p dynamic range. So, first calculate third order intercept point. The moment I know 1 dB gain compression point, add 9.6 dB. So, my third order intercept point is this. Now, I know what is my spurious p dynamic range. It is 2/3 of this POIP plus this minus this POMDS. Just previously you see we have got that formula, POIP minus POMDS, 2/3 of that. So, that you can calculate that 2/3 of this. So, that turns out to be 48 dB. So, it says that even though the dynamic range is 62 dB, I should from the noise floor or maximum usable detectable signal range POMDS, I should go only up to 48 dB. I can change the level, but above that if I do, then I will have the distortion etc. in the system, because third order intercept point will come. That means, third order modulation product will also be present with me. It will also have significant value. I won't be able to distinguish between them. So, there will be distortion in my amplifier output. So, that completes the this analytical characterization of the nonlinearity. Then we will see that these are all calculations, but if in any amplifier we want to measure it, how to measure it, that we will see in the next lecture. Thank you.